Hello everyone, I'm Jansen from the Cosys-Lab research group at the University of Antwerp in Belgium, and today I would like to show you the work that me and my colleagues did on creating an adaptive acoustic flow-based navigation system with our 3D sonar sensors. So why do we use 3D in-air sonar sensors? While the parking sensor on your car could be seen as an in-air sonar, it's not very high resolution, and sonar is mostly known for its excellent underwater usage. However, we only have to look at certain species of bats and how they use their biosonar for echolocation to find their prey in difficult environments and navigate it, that there is potential in using a more advanced sonar system in air as well. And it's there that my research group found their inspiration for developing our 3D imaging sonar sensors and are still doing so today. They have served a wide application field thanks to their excellent performance in rough conditions such as fog, dust or dirt. Agriculture, mining or other heavy industry are therefore excellent application fields for our sensors. A little bit more information now about our sensors. Our 3D sensors contains an irregular array of 32 digital microphones, and there's also an ultrasonic transducer on board to emit the sound pulse. The sound pulse is between 20 to 80 kilohertz and is ultrasonic, as I said. Now on the bottom right you can also see our processing pipeline, our signal processing pipeline. It's not very important to go into great detail on this, but what is important to know is that it's quite a computationally expensive pipeline. As such, in the past we were often limited to only using one sensor and not achieving a very high resolution due to how heavy the computational requirements would be. However, thanks to the work of me and some of my colleagues, we've been able to remake this processing pipeline on the GPU of a computer and therefore allow us to achieve a much greater resolution at a much higher measurement frequency on, for example, an embedded platform like an NVIDIA Jetson GPU. So on this image, for example, we have implemented NVIDIA Jetson GPUs on the inside of this case, which are capable of processing the sonar images at, for example, 10 Hz with quite high resolution. So the goals of the research today is that we can now use this GPU processing pipeline to place multiple sensors on our robot and still achieve real-time performance at a high resolution. This allows for a greater spatial awareness around our robot thanks to the larger field of view that multiple sensors or multi-sonar gives us. And furthermore, we didn't want to limit ourselves to placing, for example, one sensor forward and one to the left and one to the right. We wanted to allow the user to add as many sensors as they wanted and place them wherever they needed. And as such, as is on the image, you can place them wherever you want on the vehicle and just simply define them by its coordinates. In this research today, we provide the underlying theoretical base as well as do a numerical evaluation to make sure it works. So when we talk about acoustic images and acoustic flow, what are we talking about? Well, our sensor produces acoustic images, which we will also be defining as energyscapes. One such energyscape, for example, you can see here on the right in the video. And so while the small robot is driving through this corridor, you can see the reflections within this 2D representation of our world. So on the x-axis you can see the azimuth and on the y-axis the range. And as the vehicle is moving through this corridor, you can see the pattern that these reflections have. We also call these the cues of the flow. And so as such, you can see this pattern in the reflections while it's moving through this corridor. And it's this pattern that we will try to arrive to an equation to basically predict how these reflections will move through our spatial images while we have certain behavior like driving through a corridor. It's the same principle that we also see with other sensors such as cameras to, for example, do optical flow. So now we will try to create an acoustic flow model, basically predicting how these reflections will move in our spatial images based on the ego motion of our vehicle inside the sensor reference frame. And I won't go into great detail on how we arrived at these time derivatives, but this is all based on this one single formula. So if we fill everything in terms of the reflection coordinates, the linear velocity, the rotational velocity, we get to our final formula, which again is the velocity field of our reflections from the sensor reference frame. But in this case, we limit ourselves to 2D, so elevation does not matter. We can do this in full 3D, but to make the formulas more simple to work with, in this case, we restrict ourselves to 2D. And so based for any sensor placed anywhere on the vehicle, as long as we restrict this to this 2D plane, we can now use this formula to predict how the reflectings will move in our energyscape based on the vehicle's motion. However, we can go a bit further to make things easier for us and look at a few specific cases. For example, if we only have linear movement forwards or backwards, so no rotation around the axis, so omega is 0. Well, if we fill that into our formula and go a little bit further, we get to a closed loop formula that is very handy to use. I will show you an example. So in this case, we only have linear movement forward or backwards. And for example, in this vehicle where we have 3 sensors placed, one looking forward, one looking to the right at an angle, and one looking to the left, we can actually start based on, for example, this reflection A and B, predict how these reflections will move through our spatial image if we only move forwards. So for example, for sonar 1, this reflection A and B will move across these green and red lines like you see on the image. And it's this way that we can start making these models or these masking these areas within our energiescapes, within our spatial images, to predict how reflections will move. We can do the very same for only rotational movement, so where the linear velocity is 0 and where we're simply rotating around our axis. We can once again simplify the formula, as you can see, and once again, if we start drawing this out on our energiescapes, we can predict how reflections A and B or any other reflection will move across these lines. And this will help us further along, as I will show you later. So then we get to the autonomous navigation part of the research, where we basically developed a layer control system with several behaviors that will be activated when needed. And so this layered system is based on the subsumption architecture by Brooks, as many of you will already know about. And so the system needs input motion commands for the vehicle, which can be from an operator or, for example, from a global navigation system. And these will be modulated by the several behavioral layers to get to the final output motion commands. And the input to these behavioral layers, of which we have 4, is our energiescapes, our spatial images coming from our several sensors, as well as sonar layer masks. And so what are these masks? Well, they're being defined by regions. As you can see on the top image on the right, we have these regions for each layer that once reflection energy can be found in these regions above a certain threshold, we will be activating one of these behavioral layers. And it's thanks to these time derivative formulas that I discussed earlier that we can define these shapes with circles, trapezoids, lines, and rectangles to basically create masks within our sonar spatial images, within our energiescapes, to know when a reflection is in one of these regions. So it's that translation between the regions defined around the robot and the time derivative formulas to arrive towards these masks. And so to go a bit further into these masks, so we generate our sonar images on the one hand, our energiescapes, the output of our sensors. And so we multiply these with these masks, and we propose in our research to use ternary masking. So not only knowing whether a reflection energy is within the mask or not, so a 1 or a 0, but also to know whether the reflection is on the left side of the vehicle or the right side of the vehicle. This will make it easier in our behavioral layers to know to move to the left or the right, for example, to avoid objects. So looking at the first layer then, the most simple with the smallest amount of complexity, it's simply collision avoidance. So as soon as there's reflection energy within this small half circle region in front of the vehicle will stop and rotate around its axis until it's clear of the obstacle. So this is very simple behavior to avoid collision as a last line of defense. However, we rather not get to this far, and so we go to the second layer, which is activated first, which is actually obstacle avoidance, which is a bit more proactive. So the zone defined is a bit larger, and basically it will say if we keep moving forward at this velocity, we will hit this object. And so when it's activated, it will just simply move around it. The next layer is reactive corridor following. This is to create the initial alignment with a corridor. So what it does is it tries to equalize the reflection energy in the left and right peripheral regions around our robot. And so it steers away from the area with the most reflections and basically aligns itself with the corridor. And why is this important? Well, it's to activate our next layer faster, which is acoustic flow following. So this layer works a little bit differently. So it's not simply a region defined by a shape around the vehicle, but these lines, we call them flow lines. So this layer works by looking at the total energy along one of these flow lines. So basically calculating the integral of all the energy along one of these lines. So you have to imagine a vehicle driving alongside a wall. All the reflections that are on that wall will be on one of these lines if one is driving parallel to this wall. And so if we calculate a lot of energy on one of these flow lines, then we know that we're parallel to a wall. And so if we find such a peak, one of these flow lines has such a peak, then we can activate single wall following behavior. And it will try to continue following that wall at the distance it was already at. If we find two peaks that are parallel to us, so one is on the left side and one is on the right side of the vehicle, we can know that we're inside a corridor, and it will simply try to once again equalize the energy on the left and the right and stay in the middle of the corridor to navigate safely and follow it all the way. And so if we combine all these four layers, we can get safe navigation behavior. And so we can start experimenting, which is what we did. We use a MATLAB simulation of the robot, the world, and our sensors. And in order to look if our multi-sonar system works, we defined 10 different multi-sonar setups, where we have up to 3 sensors, so 1, 2, or 3 sensors activated at the same time, with various positions and rotations applied. We integrated a simple waypoint navigation system so that the robot also always tries to drive the same environment in the same way. And each one of these configurations was run 15 times. And so I will quickly then go towards a video of our results. This is one of the environments that we tested. And as such, on the top, you can see a schematic of the 10 systems that we used. So each one of these dots is a sensor, and these lines represent where the sensor is looking. And so we're going through each one of the 10 setups and looking at how the vehicle runs for that setup through the environment. And so it drives from waypoint 1 to waypoint 2, while on the right you can see the energyscapes being simulated, as well as these flow lines being found, as I discussed before. And while you cannot really see it very well, when the vehicle drives, you can see the colors of the path it is driven, and basically the color says whether it's doing acoustic flow navigation, whether it's doing object avoidance or collision avoidance. So here you can also see one of our results, which is a heat map of that same environment with all the runs laid over it. So we observed no deadlocks or collision. We had stable navigation behavior. Another important conclusion that we could make is that we accomplished spatial navigation without explicit spatial segmentation. Furthermore, by creating this modular and adaptive approach throughout the project for both the time derivative formulas as defining the regions around the vehicle and creating the masks and so on, we can use the system on any mobile platform independent of the configurations of the sensors, which is very nice. In the future, we would like to add more complex behavior, for example, when near specific objects, such as, for example, charging stations, doors, or elevators. And furthermore, with now the numerical evaluation completed, we can now move safely to a real-world mobile platform and perform full analysis of the navigation system. And potentially integrated this local navigation system in a global system with other modules taking care of path planning, task scheduling, and global navigation. Thank you for listening, and I will now answer a few questions.